Another application of our derivative is really finding our gradient everywhere. We know that derivative is the gradient. And so if we think about what we call stationary points, or what we used to call turning points, stationary points occur whenever the derivative or the gradient is zero. Okay, so here the gradient is zero, the gradient is zero, the gradient is zero. Okay, so I guess there's three types of stationary points. We've got this one here, which gives us a maximum value. This one here, which gives us a minimum value. And this one here, our point of inflection. Okay, so that's like our cubic graph. All right. So let's think about what that derivative offer into the context of problems. So the displacement, so how far a particle has travelled is given by x equals 9t minus a third t cubed between 0 and 3 root 3. Find the maximum displacement. Okay, so if we were to sketch that displacement, we've got time, I've got x of t, and x is equal to, if I factorise it, a fraction. Let's get rid of that bracket just there. X is equal to, let's take t out the front. That leaves me with a 9 minus 1/3 t squared. So clearly I've got intercepts at 0. And if 9 minus 1/3 t squared is equal to 0, 1/3 t squared is equal to 9, t squared is equal to 27, t is equal to plus or minus the square root of 27, which is root 9 times root 3, which is 3 root 3. Gives us some significance to that value there, doesn't it? So positive 3 root 3 and negative 3 root 3. So it's a negative cubic, so the general shape is that one there. Yeah. Well, clearly out here we don't need, so my graph, it comes up like that and goes out down through there. Now I'm going to stop my graph there because the domain is 0 to 3 root 3 inclusive. All right. So there's the graph of my function. I'm interested in the maximum displacement, and the maximum displacement is clearly that point there. So when does that maximum occur? Well, it occurs when the gradient is 0. So what I need is dx dt equal to 0. So what is dx dt? So dx dt is equal to 9 minus 3 times a third t squared, which equals 9 minus t squared. So there's the gradient everywhere, all right? So solve dx dt equal to 0. I get 9 minus t squared is equal to 0, t squared is equal to 9, t equals plus or minus 3. So that means my turning points, remember, if I had the rest of the graph here, that turning point would be at negative 3. This turning point is at t equal to 3. So that's when it reaches the maximum. The question is, find the maximum displacement. So that means then, let's come across, at t equal to 3, x is equal to 9 times 3, 1/3 times 3 cubed, which is equal to 27 minus a third of 27, which is 9, which is 18 meters. So that point there is the point 318. So the maximum occurs at t equal to 3, right? But the actual maximum value is 18 meters. All right, so if we're just looking to find some stationary points, so the stationary points occur, need whatever, dy dx f dash of x equal to 0. All right, so in this case, I'm going to put dy dx is equal to 12 minus 4x. So we want to solve it equal to 0. 12 minus 4x is equal to 0, so 12 equals 4x. X is equal to 3. So I'm assuming to find the stationary points, we should really have a coordinate. So at x equal to 3, y is equal to 9 plus 12 times 3 minus 2 times 3 squared. 9 plus 36 minus 3 squared is 9, so that's 18. So what's that going to be? 27. So the actual stationary point is the point 327. Okay. Let's go across here. Maybe change the colour. dp dt is equal to 6t squared minus 10t minus 4. So let's take a 2 out as a factor. 3t squared minus 5t minus 2. I'm sort of hoping this factorises nicely. We get 3t times t crossed with 2. So if I make that a negative 2 and that a positive 1, 3t times negative 2 is negative 6t. T times 1 is t. It's negative 5, so that's good. So we get 2 times 3t plus 1, t minus 2 is equal to 0. Okay, so we want it equal to 0 to find the turning points. So therefore we get t equals minus 1/3 or positive 2. So my coordinates are negative 1/3 something to something. So for example, let's put t equal to 2 back into my equation here. We'll come here. So at t equal to 2, p is equal to 2 cubed is 8, 16, 2 squared is 4, so 4 5s are 20, minus 8 plus 13, which is equal to 16 plus 13 is 29 minus 28, which is equal to 1. And at t equal to minus 1/3, which might be a bit messier. So minus 1/3 cubed, so we're just going to cube the top and the bottom, is negative 1 on 27. So that's negative 2 on 27. Minus 1/3 squared is 1/9, positive 1/9, so it's minus 5 on 9. Negative 4 times negative 1/3 is plus 4 on 3 plus 13. Hopefully we've got a calculator. Let's turn them all into 27ths. So we get everything on 27. So I get negative 2 multiplied by 3 is minus 15. Multiplied by 9 is plus 36. Oh dear, we'll just make it plus 13, I think. So we get, what's that? Negative 17 plus 36 is positive 19. Is that right? It is. So we get 13 plus 19 on 27. So let's write it as that, 13 and 19 on 27. All right, so that's the coordinate of that turning point. So they're my stationary points. And for C, hopefully there's enough room in here. dy dx is equal to 3 minus 3x squared. Solve equal to 0. Oop. So I get 3 minus 3x squared is equal to 0. 3x squared is equal to 3. X squared is equal to 1. So x equals plus or minus 1. So there's my two solutions, or my two stationary points. If I put x equal to 1 in here, I get 4 plus 3, which is 7, minus 1, which is 6. If I put negative 1, I get 4 minus 3, which is 1, minus a minus, which is a plus, so 2. All right. So to calculate stationary points, we need to find our gradient, and where the gradient is 0, we find our derivative. All right, what's our last one? Our last one talks about the curve of the equation of that passes through 0, 5 with stationary point 27. Find A, B, and C. So what information? We've done a few of these find the equations before. Here's one piece of information. So at x equal to 0, y equals 5. So substitute that in. So equation 1, 5 is equal to x equal to 0, 0, 0, 0, C. So that's a good start. There's another point the line goes through, the point 27. So equation 2, y is equal to 7 when x is equal to 2. So 2 cubed is 8 plus 2 squared times a is 4a. 2 times b is 2b plus c, and c is 5, so I might as well put that there. So I can change that and modify that to 8 plus 5 is 13, take it across, I get negative 6 is equal to 4a plus 2b, so there's an equation. Now, what other equation? Another point. What bit of information haven't I used? I haven't used the fact that it's a stationary point. So what does that mean? If it's a stationary point, so the stationary point means dy dx is equal to 0 at x equal to 2. So find dy dx. Dy dx is equal to 3x squared plus 2ax plus b. And at x equal to 2, the answer should be 0. So I'll get 0 is equal to 3 times 2 squared plus 2a times 2 plus b. So I'll get 4a plus b is equal to 2 squared is 4, 4 3 is 12, negative 12. So there's my second equation. So let's put over here, negative 12 is equal to 4a plus b. Let's subtract. 2b minus b is b. 4a minus 4a is 0. Negative 6 minus a minus is plus. So it's plus 6. So b is equal to 6. So if b is equal to 6, substitute it into, I might pick this one with positives. That means then that 4a plus 6 is equal to negative 12. 4a is equal to negative 18. A is negative 18 on 4, which is negative 9 on 2. And there's our calculator solutions. The function, we define the function up here. I'll work out the derivative of the function at x equal to 2, and I get that little equation here. So then I've got three equations. The function at 0 is equal to 5. The function at 2 is equal to 7. And that derivative equation is equal to 0. So three equations, three unknowns, gives me my A, B, and C. All right, off we go.